I think we can start. Okay, so this is a heavy job to start with the first talk after the social dinner. Anyway, I hope you can stay up. So this lecture was taught to give you an introduction to the evolution of scientific libraries for numerical linear algebra during the last 50 years. And I will give an introduction starting from the LIMPACT benchmark. That is a good occasion to understand what is LIMPACT exactly and what is exactly the benchmark we run in order to rank the supercomputers in the world. And starting from the LIMPACT benchmark, I will start discussing the driving issues to which the evolution of linear algebra numerical software has to be applied in order to use at the best the supercomputers. And main player in this evolution has been the group of Professor Jack Dongara, now Professor Emeritus at the University of Tennessee, Knoxville, Turing Prize 2021. And indeed, I used some slides from one of his collaborators, Mark Gates, that taught some lessons on linear algebra numerical software evolution in the class given by Jack Dongara. So let me say that at the last day of this school, you know very well what is top 500 list. You can see that in this list was the last version has been presented at the last conference of International High Performance Computing Conference in Hamburg in the first week of June. We have three different, in the top list, we have three different supercomputers installed in the United States, and all of these supercomputers are based on some architectures that are heterogeneous. They use CPU that are multi-core and are accelerated by using different types of GPUs. So let me say that the ranking is based on the column that here we can recognize as the column of R max. What is R max and what is R peak? You know now that R peak is the theoretical performance. This is a number that was given by the vendors and is a paper competition measuring by counting the floating point operation in full precision that the architecture can do. All the cores of the architecture can do some floating point operations at a given speed, theoretically. Anyway, this is a roof line. R max is the measured performance of the supercomputers based on the best results by solving a linear system, a dense linear system. This is the LIMPACT benchmark. Let's say that the original LIMPACT benchmark appeared as a test case of the first numerical library for scientific computing, whose name was LIMPACT. This was a code for solving a linear system of size 100 by using the Pigit function that factorized the matrix by the Gaussian elimination applying pivoting, partial pivoting technique, and the results, two triangular systems, were solved by using backward and forward substitution algorithms. I suppose that you can be familiar with this type of algorithm. And you know that partial pivoting is essential for stability of Gaussian elimination, and that starting from a matrix, we can solve the system by using the partial pivoting in a way that PR x is equal to LUX, where L is a triangular matrix with a unit diagonal, and U is a hypertriangular matrix, so that the resulting system is LUX equal PB, so that you can obtain X by solving this, and epsilon is obtained by the data by solving two triangular systems, the first one by using forward substitution and the second one by using backward substitution. Forward and backward substitution are optimal algorithms for solving triangular systems. You do n squared half operation on n squared half data, okay? So this is the objective of LU factorization, and LIMPAC is based on the algorithms that solve the system this way. You have to know that LIMPAC is not, the LIMPAC benchmark is not exactly the code for solving 100 unknowns. That is the code that was in the user guide of LIMPAC software. But now we use a version of LIMPAC that is named High Performance LIMPAC toward Peak Performance. That is a version of the same algorithm for distributed memory parallel computers by using the node in the case of full memory using, okay? So the size of the problem is the largest possible by using all the memory available on a core, and the version of the linear solver is a parallel version of a Gaussian elimination. So let's go inside to LIMPAC. LIMPAC was proposed in 1979, was written in Fortran, and this library has the objective to solve in an efficient way linear algebra problem for dense and banded matrices. Dense matrix is a matrix that has almost all the entries different from zero. On the other hand, triangular, is a matrix in which some part lower or upper, the main diagonal has all the elements equal zero, and banded are matrices in which the structure of the elements of a non-zero element are based on some different diagonals in a band. So what was the objective of LIMPAC? The objective of LIMPAC in the mind and of Jack Dongara, that was very young at that time, and worked in Argonne laboratories in Chicago, the main objective were the performance and portability. So before starting to write the LIMPAC package, the group of numerical analysts collaborating with Jack proposed some application programming interfaces whose name is well known as Basic Linear Algebra Subprograms, BLAS, Level 1 BLAS. Okay? So, a lot has happened since then, and we would like to understand what is HPL TPP. That is not exactly LIMPAC. many things what happened, and there is a very nice paper that was related to the lecture that Jack Longara gave for his Turing Prize in 2001. I propose you to read this paper since it's very, very interesting. The paper traced the evolution of numerical algorithms following the evolution of the technology during 50 years. Okay, and the main message of Jack Longara was that generally it is not sufficient to refactor legacy code and legacy library. It is needed to rethink the algorithm in order to face the new issues coming from the technology. And so new mathematics, new numerical methods, and new implementation design patterns are needed to use at best the available technology. Okay, so let me give some introduction to the basic linear algebra problems to whom of you that are not familiar with this concept. Linear algebra problems arise from many contexts, and not only in scientific computing and numerical simulation, but also in more recent machine learning and artificial intelligence context. Usually, the main problem that is has been recognized as the 70% of the building blocks in numerical simulation and computational science context, and is the main computational building block usually, is the solution of a linear system. The solution of a linear system comes from usually from discretization of some continuous problems by partial differential equation. On the other hand, a linear system can come also for solving nonlinear problems by application of a Newton type algorithms for linearization, and many times also comes from optimization problems by applying some distant algorithm, gradient descent problems, and applications where we have to solve some recurrences. We have to apply some recurrences based on the concept of a gradient of the function, the nonlinear function, the action of the nonlinear function. So linear system is transversal, has a problem. Some other linear algebra problems come from the eigen problems that are main computational kernel in structural mechanics, chemical engineering, but also in network analysis, for example, in clustering. In this case, you have to find eigenvalues and eigenvectors of a matrix. And another main problem in numerical linear algebra is singular value decomposition, that is a generalization of the eigen problem. And it is applied, for example, many times in data compression and data reduction dimension, where we want to get main information from large set of data. So what are the algorithms that we use for solving linear systems? Let's say that we need to understand what is the structure of the matrix, and I will give you a discriminant in a few minutes. The best and well-known algorithms are algorithms based on backward and forward substitution. In the case A is triangular. When A is general and non-symmetric, usually we use Gaussian elimination, that is LU factorization, or QR factorization in the case, for example, A is very Hill conditional or is not square. In the case A is a symmetric positive definite, symmetric with all the eigenvalues real and positive. Let me say that I am discussing about matrix with real data. Anyway, all I am saying it is can be said also in the case A is a matrix with complex data. In the case A is symmetric indefinite, usually, and the symmetric positive definite or indefinite, we use some variants of Cholesky factorization. And in case of over of or underdeterminate systems, we need to apply some QR factorization in order to find the minimal residual solution or the solution with minimal norm. Okay, so the basic algorithms are factorization of the matrix. In the case of eigenproblems, we need to, in turn again, distinguish between general matrix, non-symmetric, or symmetric matrix in order to have gain from the structure of the matrix, and some QR-based iterations are the main algorithms. Also, in the singular value decomposition, the main algorithms are QR factorization. QR factorization, I don't know if you know, is Q is an orthogonal matrix in the case of real data. And so its transpose is equal to its inverse, and R is an upper triangular matrix. So you can apply QR in order to solve system, first by modifying the right-hand side, applying Q transpose, and then solving a triangular systems by applying a backward substitution. Another main discriminant to use the best algorithm for solving a linear system or for obtaining eigenvalues and eigenvector is related, as I already said, on the density or sparsity of a matrix. Dense matrix, I said, is a matrix having working on n square. If n is the dimension of the matrix and we consider the matrix square, n square is the number of entries, and we need to compute on all the entries of the matrix in order to obtain the solution. On the other hand, sparse matrices have a lot of entries equal to 0. In this case, we need to obtain some advantages by using a special type of data structures and a special type of computation that avoid to modify the matrix in order to do the lowest number of operations on the data we are. Okay? And in the case of compressible data, we need to use some hierarchical approaches in representing the matrices, the data, and also in doing operation, for example, by using some low-rank representation of small dense blocks that don't have inside a lot of information, and that we are in the situation in which this information can be compressed and obtaining some approximation in the solution with a given accuracy. Okay. Let's go to the driven issues in the evolution of the numerical libraries for solving linear algebra problems that we discussed until now. The basic driving issue is related to the memory model that has been implemented in the modern architecture. You learned many things on this topic in the past days. You know that NVIDIA is working a lot in order to have a shared memory for a large number of GPUs, to have a very large bandwidth, and to share data and to communicate data to the unit logic arithmetic unit in a quick way. Anyway, here is an example of the memory model we have on Intel CPU. This is a Haswell third generation of Intel microprocessor, but the same model is applied in modern microprocessor technology. And we have a lot of levels in which the bandwidth is very different. The rate of data communication between the different levels of memory and CPU, the arithmetic logic unit, is different and depends on the level in which we store the data. There are different levels of cache, and the faster is communication if the level of memory is very close to the CPU, okay? So the same model is applied also in GPU. I don't give details since you are familiar on the structure of the memory also on modern GPU, where you have some type of shared memory levels inside the symmetric multiprocessors, and you can have some cache memory that are shared by all the symmetric multiprocessors, and you have the global memory, and all these memory are characterized by different latency and different bandwidth to communicate and to access data. So the roofline performance model is what drives the evolution of the software development, since it is very simple. The velocity for operation, that is the number of floating points of operation per second, can be written in this form as the product of what we call operation intensity, that is the ratio between the number of floating point operation that I can do on a word, on a memory word, and the velocity, the speed for accessing data, that is the memory bandwidth. So if I want to do a lot of floating point operation in a second, I have to increase operation intensity, or I have to increase memory bandwidth. So for a given technology where memory bandwidth is fixed, for example, on Frontier, on Leonardo, where we know what is the technology and what is memory bandwidth, we need to use at the best the floating point throughput of the processor by increasing operation intensity. This is what we can do at the algorithmic level. And we have to organize our algorithms and our code in order to have the maximum operation intensity. Let me say that I am using some slides that I already have seen yesterday, for example, in the presentation of Didier. These are the driving forces of our work. You know that while the floating point operation speed increased very quickly in the last 50 years, there is a gap in the memory bandwidth increase. And this gap can reach also 2 orders of magnitude. I read in a paper from the Spinetta guys that the gap between the global memory of a GPU of Leonardo and the memory, the bandwidth of the global memory for accessing the data in the global memory shared by the symmetric multiprocessor available on the GPU of Leonardo is 1 order and more of magnitude less than the operation speed of the GPU. Okay, so we need to consider this gap in order to have efficiency by using the GPU of Leonardo and all the floating point throughput that is available in order to use at best the money of people for buying. So this is a slide in which we can see that the gap between floating point speed and memory bandwidth was increased from 1985 between 15% and 30% per year. So in this band of this plot, we can recognize some architecture essentially available before 19 years, in which there is a good balance between flop rates and memory bandwidth. And in this case, usually we say that these architectures are well and are good when our algorithms are based on vector operation, because they find their velocity, their speed by using some single instruction multiple data model and vector instruction set in order to do the same operation on a large bunch of data in a quick way. Okay. In the other band, that is the representation of the modern and the current technology, vector operations are not sufficient. We need to organize the algorithm in order to use dense blocks. Dense blocks are what we call the blast tree operation. Okay, blast tree is the level 3 of blast and is the evolution of the application programming interfaces that was taught for classifying and having a taxonomy of linear algebra operations based on the number of floating point operations we can do on some data, on a given set of data. So let me give you some more details on basic linear algebra subprograms. As I already said, they were introduced by some numerical analysts and mathematical software designer in the end of 17 years, and were published on the main journal for mathematical software designer, that is ACM, Transaction on Mathematical Software. And these are operations that operate on vector. So all the data present in the operation are vectors or scalar. So they work on n data, if n is the dimension of a vector, doing operation whose complexity, theoretical complexity, is linear in the dimension of the problem. So in this case, the operation intensity is n to n. So is 1, is constant. So increasing the dimension of the vector, we do a constant number of operations. So this is not a good situation. We move one data and we do on this data only one operation. And taking into account the gap between memory access time and floating point speed, we are in a situation that is not good in terms of execution time. This was good in 17 years when LIPAC was written. Indeed, in that time, we already have some type of supercomputers like Cray based on vector technology structure, SIMD, SIMD programming model, and BLAS1 was sufficient to use as the best technology. Now it's not sufficient. We need to go up. We have another level, basic linear algebra subprograms of level 2. This was taught later, following the evolution of the architecture. And in this case, the basic operation is matrix vector product. We have as data a matrix and a vector. The number of data are n squared if matrix A is considered square. And another basic operation of BLAST2 is the backward or forward substitution, characterized by n square onto half n square theoretical performance. So also in this case, the operation intensity is 1. These are operations that in the language of the roofline performance model are known as memory bound, since the time to have data is larger than the time to execute the operation, also depending on the number of operations we are doing. So BLAST2 is not sufficient again, and we need to go up in the level of operation. And the best level we can define at the moment for linear algebra problems that we know is the matrix multiplication. What is the advantage here? The advantage here is that we have n squared data, but the basic algorithm for doing a matrix multiplication between two dense matrices requires n cube operation. Finally, we obtain what we are lucky to attain, we are happy to attain. Indeed, we have an operation intensity, n cube on n square, that increase with dimension of the problem. Linear increase with the dimension of the problem. This is a very good feature in order to use at the best the floating point throughput of modern architecture, especially GPUs. And we want to define all our algorithms for doing linear algebra and for solving linear algebra problems in terms of BLAST3, since in this case it is known that we can use at the best the technology. So here there are some picture to understand the performance of the different levels of BLAST. The basic operation of level 1, is the scalar product between the two vectors. In this case, the complexity is linear in n, but also the memory traffic. And the typical gap between BLAST1 and BLAST2, where the basic operation is the matrix vector multiplication, is of the order of 10, one order of magnitude. If we give a look at in the right of the picture, you can see that the gap between level 1 and level 2 BLAST and the matrix multiplication, GEM operation, that is the basic operation of the level 3 of BLAST, obtain also a gap of around 26 speed up. Okay, so we need to use GEM in double precision or in single precision in order to have the best performance by modern processors. So we want to formulate our algorithms in terms of BLAST3 since it is efficient, and there are a lot of advantages that are not only related to performance, is only related to the fact that BLAST operations are a standard application programming interfaces. In that paper, you can find the reason to tell this type of interfaces in a given way, and all the vendors have the opportunity to implement at the best this type of operation for the architecture, optimizing the operation. So there are also some open source implementation available on the netlib, for example. And we have to consider that writing a code on the top of a BLAST makes it portable further than efficient. So you can use this by compiling towards BLAST available on your machine. And you don't have to reinvent the wheel. every time. So let me say that you don't need to write any algorithms for implementing a matrix-matrix multiplication, since it is well done by basic linear algebra subprograms implementation in some libraries available on your computer. Okay, let me go again on the LIMPAC benchmark. The LU factorization available when LIMPAC was written is based on +1 operation. It is a standard Gaussian elimination algorithm. You know what is Gaussian elimination? It is an iterative algorithm in which if n is the dimension of the matrix, in n-1 steps, you build a lower triangular matrix made by so-called multipliers, and an upper triangular matrix that is a transformation of the original matrix by linear operation. So this is the main operation. It is a scaling of all the rows that are in the so-called active matrix in different steps. It is in blue in this slide. And we run on one column per time. Given the multipliers related to the column, where we do only a scaling of the rows, we update each column of the submatrix that is called active, one column at a time, by using a AXP operation that is a vector update. Now it's an operation of the type y equal alpha x plus beta y. And the parallelism is in vector operations and is based on +1. So this is not the code that run on supercomputers in order to have the ranking of a top 500 list. What happened after LIMPAC, and what happened when we moved from the vector supercomputers to supercomputers having different level of cache memory and can do good in terms of matrix vector product or matrix products. We have here the successor of LIMPAC, that is LPAC. LPAC is based on block algorithms for dense abandoned matrices. And the aim of LPAC was to write to reformulate all the linear algebra main algorithms, essentially the LU factorization, QR factorization, singular value decomposition in terms of block tree. It includes also, as I said, on the contrary of LIMPAC, also singular value decomposition in order to obtain singular values of matrices and eigenvalues of matrices, while LIMPAC only included linear solvers. Let's say that LPAC is an ongoing project, since many new achievements are obtained in terms of theoretical aspects related to the stability of the algorithm. Since if we want to reformulate algorithms, we need to face also new issues from the numerical point of view. For example, numerical stability of the algorithms. That changes if you change the order in which you do operations. Can change. So I have to give some details, since I like that you can understand what is the main issue you are facing when you transfer the scalar approach to the blocked approach. What is the main LAPAC subroutine to do LU factorization? The name is DGETRF. This solves a linear system that is not necessarily square by using LU factorization, a blocked version of LU factorization, applying the partial pivoting in order to have a stable Gaussian elimination. And so we obtained a permutation matrix, a lower triangular matrix, and an upper triangular matrix. In this slide, I put in red the so-called factorized panel, since the algorithm again is based on an iterative approach in which we start by factorize a column panel. Then the idea is to update the corresponding row panels and then repeat the same process on a sub-block matrix. That's the right lower part, by using the same approach, and we named indeed this type of submatrix as the active matrix. So in red, I have the factorized panel, and in blue, the row block to be updated at a given step, and in black, the active matrix. Let's consider that I put the matrix in terms of a 3 by 3 block matrix, in which I am consider some splitting blocks of row and column, the original matrix, in which all these blocks are a given dimension, for example, NB times NB, where NB is the number of row and columns inside one block. Okay? In the following, I will give some details on the possibility to reformulate the Gaussian elimination in terms of a block algorithm. And let's say that I use as a permutation matrix the name PI, depending on the step I am working on, and I don't consider formalization in terms of dimension of this matrix. Okay, so let me use PI also if dimensions are not well specified. So at the first step, we have factorized the first column panel, okay? And all the sub-blocks that are in red have already computed by applying a standard Gaussian elimination, by computing multipliers for all the rows, and by factorizing the first A11 square block, okay? And having computed all the multipliers related to all the rows in the first column panel, okay? So all the blocks in red are already computed. When you have this, you can obtain equalizing the first row of the first terms in that equality with the first rows obtained by computing the matrix-matrix products between the lower triangular and the upper triangular matrix. So P1, A11, A12, A13 has to be equal to L11, U11. That is first row by first column of the second term. L11, U12, L11, U13. Okay, this is good since we need to have this equality, and indeed we have L11 and U11, that is factorization of the block K11, where P1 is the related permutation matrix. And then we have to obtain this in order to update U12 and U13. But L11 is known, and L11 is the lower triangular. So if P1, A2 we have, and L11 is already computed, we can obtain U12 and U13 by a blocked version of forward substitution, solving a linear system with triangular matrix. So this is the blocked version of the step that we called the update of a block of rows. In LFPAC or blocked style, Gaussian elimination. So let me show these formulas that are not so difficult as appear, since we can obtain the same way the update of the active matrix by using matrix multiplication. Indeed, by the equality of this product with this matrix, we obtain that L22U22 is equal to P2A22 minus L21 dot 112. These are two terms that are already computed, and this is a matrix multiplication, and this is an update of a block of rows. So these are all operations of level 3 plus. So we are happy. Indeed, the blocked form of triangular solve and matrix multiplication involving dense matrices are good to obtain a large operation intensity. So we can repeat this process by using the active matrix. We can compute by applying +2 operation the factorization of the current column panel, and then starting from L22 and L32, we can update the block row, the current block row, by triangular solve, and update the active submatrix by matrix multiplication. Okay. So we have a good solution in the case of shared memory architecture, okay? TPP, HPL TPP is not LPAC. It's not LINPAC. It's not LPAC. What is? How to move these algorithms in the direction of distributed memory machine, since Frontier, Leonardo, and all machines, including the top 500, are distributed memory machines. So LPAC is not good for distributed memory machine. Our matrix usually has a dimension that will go beyond the memory of a single node. So we need to apply a new approach in order to move the blocked form of the Gaussian elimination towards distributed memory machine. Okay. So we have another problem related to memory access. If you want to work on a distributed matrix, you need to move data along a network. So we have another level of communication in a multi-node system where distributed memory is the standard model. We need to consider the execution time is the addition of 3 elements, where we have the time for operation, the time for accessing the local memories, and the time for moving data along a network. So in the case of TMM and TCOM, the model is the same, since we need to consider the number of messages and the number of data we move, and the time for accessing shared memory is given by the number of words to the memory bandwidth plus the number of accesses dot the memory latency. And the same is for the network. I used a table coming from some slides of Professor Laura Gregory, that is another expert in numerical linear algebra for HPC. And here we have the percentage of increasing in speed of processor in doing operations in the last years, and in 1 year in the last period. And here we have the increased ratio of network bandwidth and latency bandwidth. The gap is again here. So we need to consider some algorithms that are able to do operations without, possibly without moving data on the network. And indeed, in this moment, for example, Laura Grigori is a very expert in communication avoiding LU factorizations. It is a very interesting chapter of linear algebra for HPC. And so many times it is better to recompute something and to replicate operations on different processors instead of moving data out the network, okay? In some cases. So in the 1995, using again Fortran language, modern Fortran, the guys related to Jack Tongara and his group introduced another software, mathematical software project whose name is Scalepack. Scalepack is the acronym of Scalable Linear Algebra Package, and is a version of LPACK for distributed memory machine. The main feature of this library is related to the way the data, the matrix data, are distributed among the different memories, different processors. The algorithms are again a type of a blocked algorithm, since we need to use at the best the single processor, and we need to move at the best. We need to move less data as possible, okay? As less data as possible. And we need also to balance in a good way the work among the different processors. You have seen that LU factorization during the process shrink the data on which we have to compute. So we need to focus on the way we distribute data among parallel processors in order to use all processors during the process, computation process, and avoiding to leave some processor idle. Okay. So in this case, the main approach was a block cyclic data distribution. In the case of algorithms such as LU factorization that shrink the matrix during the process, and the block data distribution in the case of banded matrix, since it was demonstrated that it is not needed to do a block cyclic distribution. And a version of Scalepack is available online on NetLib. And this is an ongoing project for the same reason I have already said for LFAC, since many types of new achievements are obtained during the years, and many things have been dealing in order to have for example, new approaches such as randomized algorithms and randomized singular value decomposition that are the state of the art for doing well linear algebra computation, for example, in machine learning and artificial intelligence context. The way they organize these new software libraries is modular, and the authors, the designers, decided to put all the basic operation in components of low level that they named P plus. P plus is parallel plus. So all the operation or the basic operation involving blocks of matrices are made at the level of P plus. The main operation is the distributed memory matrix multiplication. And there is an interesting new parameter in the application protocol interface that is related to the so-called matrix descriptor that includes information on the matrix data distribution since the new thing in the distributed memory machine is the way you have to consider distributed matrices. All the data communication that have also a standard pattern in this type of algorithm are implemented in another low-level library on which scalepack is based. The advantages to use this type of modular approach is, of course, the portability and possibility to implement at their best to optimize these low-level kernels to expose functionality to the higher level algorithms. And the other kernel is basic linear algebra communication subprograms. They are linear algebra oriented methods passing application protocol interfaces, usually are implemented on the top of MPI, of course, but can be implemented also on the top of some other communication library, for example, implemented by the vendors, the machine. And the logic is that all the processes that you want to consider in an MPI context are organized in terms of a logical 2D process tree. And in this way, each process is identified by a couple of indices, and all the collective operation in terms of data communication, global communication operation, are organized as collective that are made on a row of a process, on a column of a process, or on the global process tree. Okay? So this is an example on the way the processes are mapped, for example, on a 2x4 process tree. We have 8 processors. Each one is characterized by a couple of indices as in a mesh, in a geometrical mesh. Okay, this is only a logic representation of the processes that can be obtained by using a basic functionality of MPI. Maybe yesterday you have some information about the possibility to define a linear ring or a process, a 2D process grid by using application protocol programming interfaces from MPI. The matrix can be partitioned in a different way on a logic 2D process grid. For example, we can use a 2D block cyclic that is good for good balancing, load balancing, and good computation to communication ratio when matrix shrinks, as in the case of LU factorization. And this is what we have in this picture. We can define the dimension of a small block, and we can assign this block in a cyclic way along the process grid. Okay? In this way, when the matrix shrinks, all the processes are involved in the computation, also if the number of blocks is decreased during the computation. Okay? In the other case, we can consider, in some other case in which it can be useful, we can consider cyclic distribution by columns or by row. Okay? In the picture half, you can consider some other typical data distribution that we use, for example, in some cases in which the matrix doesn't shrink during the process. It is the row block, column block, or block distribution. Okay, I don't give details on this since my time for the first part of this lecture was finished, and I can say that it's finished. I can say that high performance LIMPAC is a scalepack style LU factorization. So the code that the vendors optimize in order to rank their supercomputer is a version of LU factorization in the style of Scalepack, where they apply a 2D block cyclic distribution of the matrices. The size of the matrix is selected in order to have a memory that is used at the in the full condition. So it is the largest size possible. And the approach is an approach where all the computing nodes are working in a synchronous way, exchanging the data when it's needed, and parallelism at CPU level is in blast-free operation that are blocked triangular solve and blocked matrix-matrix multiplications. Okay. There is also a version for the modern supercomputers implementing accelerated by GPUs. There is an interesting paper published by NVIDIA guys in 2023 that describe the HPL algorithms for using at the best also GPU accelerators. This is a look-at version of the Scalepack algorithm. Look-at is a way to say that it is a pipeline version in which they work on a single block in order to factorize the block on the processes involved in the factorization of a column panel. And when the factorization is ready, they send immediately the block to the other process in a row, read, and in the column, process that are in the same column, and then they compute for updating the block of matrices that are in the local memory in order to update the local block. Okay, so the project for writing linear algebra scientific libraries are in progress. The Jackson Garrett team is working on plasma, on magma, on slate more recently, and these are all the successors of Scalepack. Plasma is a project started in 2008. And the main focus is using at the best multi-core processors. Magma is focused on the use at the best GPU accelerators. And more recently, the group of University of Tennessee and some other groups from other USA university are working on a new project named Slate. Slate is software for linear algebra targeting exascale, and they are rethinking all the algorithms in order to take into account all the new issues for using in a good way, in the best way, the hierarchical supercomputers that vendors are proposing for facing this new challenge that is to obtain exascale algorithms for exascale machines. Okay, so I finished this first part, and I would like to conclude to say that the lesson learned from the last 50 years linear algebra software project is that the cost of data movement dominates the cost of floating point arithmetic. So we need to rethink all the algorithms in order to reduce memory access and data communication. Accelerators can run at very high throughput, exploiting high level of data parallelism, and many times having efficient use of these accelerators require to substitute more accurate methods with more parallel ones. For example, this is the case of randomized algorithms for linear algebra or some iterative processes for solving sparse linear systems that I will face in the next lecture. Accelerator work very fast on low precision, and so usually in the last period, numerical analysts and computational mathematicians are trying to propose some old algorithms for doing computation by using low precision arithmetic in order to attain higher precision during the computation, applying, for example, the so-called iterative refinement approach that was already introduced many, many years ago by Wilkinson. And minimizing energy consumption is an important issue for sustainability of high-performance computing. And in this case, of course, the basic guideline is to reduce the processing time. Okay, and reducing processing time is related to the best use of processors' capabilities. Okay, so I think that we can do a break now, but let me say that what I was focusing today is that is something that was that is not new. An interesting letter of von Neumann to Maxwell Newman in 1946 read that the methods of approximation mathematics will have to be changed very radically in order to use effectively the computer, the modern computer. So when you introduce a new technology, refactoring of existing code is usually and generally not sufficient. We need to rethink the algorithms. And when you rethink the algorithm, many new issues in terms of theoretical aspects, for example, numerical stability, have to be dealt with. The same is said by Jack Tongara in the current period. In this interesting paper, Jack said another interesting thing. The design of numerical algorithms and mathematical software is an interdisciplinary scientific contest with many features of a translation of science. As in medicine, we need to collaborate. Computer scientists and mathematicians and scientists from different fields have to collaborate in order to rethink the models and the algorithms for using at the best the current platform. Let me restart. I don't want to bore you, but I would like to give you some information related to my current research activities that are focused on sparse linear solvers. And this is the occasion to introduce the approaches, the algorithmic approaches that are useful for solving sparse linear system in the context of high performance computing. So let me thank before all the team that is at TIAC and working on HPC and also involved in my current project for linear algebra. We have some stable members in my institute that are in the main site of the institute that is in Rome, while I am in the branch of Naples. And I have some very stable collaborators with some colleagues from the University of Pisa, University of Rome Tor Vergata, and also with Flavio. They are all associated, research associated to my institute. And we also have some international collaboration that we're setting up during the years since I have been dealing with these topics for a long time. So, sparse linear system. Let me repeat that sparse linear system is a different context with respect to dense linear systems. Our matrix is very large, And the notion of large depends on the time. For example, it's von Neumann time, a linear system with 100 unknowns was very, very big. Now we are dealing with linear systems having a number of unknowns that go beyond 10 billions or also 100 billion of unknowns. And we can have this type of problems not only in numerical simulation that is a traditional context, but also in network analysis. For example, I proposed recently some algorithms based on the computation of eigenvalues and eigenvectors of Laplacian equation representing networks. You know maybe that what is the graph Laplacian, and based on the graph Laplacian, you can apply some clustering approach that use eigenvalues of matrices, and we propose some way to compute approximation of eigenvalues based on solving sparsity net. So sparsity is the main feature of our matrices, and the sparsity can be very large. For example, in the case of the standard Poisson equation on a 3D domain, you have a fixed number of non-zero elements per row. This number, the so-called stencil, depends on the type of discretization you use. And in the case of the benchmark that usually we use to measure the performance of our algorithm, this stencil can have only 7 points per row. So you can imagine what is the level of sparsity of our matrix. Where we want to run our projects are European projects or national projects to use the current supercomputer in order to prepare the application code to use the future exascale supercomputer. Okay, so we need to consider that these computers are thousands of CPU cores, GPU accelerators, and we have to apply hybrid formal parallelism to use this as best. And in this column, you can understand that solving sparse linear systems by some iterative algorithms, well-known iterative algorithms such as conjugate gradient, precondition conjugate gradient, is not so simple. Indeed, we have a very low percentage of the peak performance. For example, on Leonardo, this percentage is about 1. And we are in the situation in which we are stressing the current architecture by doing some computation where the memory bandwidth is more important than the floating point throughput of the architecture. And so maybe vendors can study, or scientists working on architecture can study the way to improve the situation, but at the moment we need to think and to formulate algorithms in order to use this platform better. Okay. So if a matrix is sparse, we need to use this sparsity during the computation in order to save memory and in order to save floating point operations. This is the definition of sparsity by James Wilkinson. That is another guy, Turing Prize. Let me say that both Jackson Garra and James Wilkinson were mathematicians and not computer science originally. Okay. I would like to say this, since mathematics and computer science have to collaborate if they want to produce science for the future. So what are the algorithms that we use for avoiding to modify the matrix? if you have done, if you, you have the opportunity to follow some class of numerical computing, you know that Gaussian elimination is not good for sparse matrices since there is the so-called fill-in phenomenon. In the case of sparsity, I don't want to fill the matrix since I don't want to change the number of non-zero elements, and I don't want to change the way I storage the matrix. So in this case, the best method are iterative processes, iterative algorithms that don't change the matrix. Usually, the iterative processes for solving systems are based on on looking for solution in a specific vector subspace, okay, of the real vectors. This subspace is known as Krylov or Krylov, depending on the way you mention. So Krylov subspace are subspace obtained by power of matrices. You start from a given solution, you compute the related residual, and you look for new solution by increasing the size of a vector space obtained by multiplying the matrix and power of the matrix A with the current residual. So the archetype of the iterative solvers for linear systems is the conjugate gradient method. That is a method applicable to symmetric positive definite matrices. Let's say that there are a lot of formulation of analogous methods that can be applied to more general matrices. You can refer to the bibliography in order to study this type of methods. Main issue in the conjugate gradient process, this is an iterative process starting from a given solution and looking for a new good solution by iterating some operations until the given accuracy or the requested accuracy is obtained. So the complexity of this method depends on the number of operations you do at each iteration, but also on the convergence. Okay, if I need to do a small number of iterations, I am happy since I paid not a lot of money to have my solution, since using supercomputers it's also a matter of money. So energy, so it's related to money. Conjugate gradient convergence depends on a factor that is named conditioning number of the matrix. This is the ratio between the maximum eigenvalue and the minimum eigenvalue of the matrix. Okay, so let me say that the choice of this precondition is the main topic for dealing with the sparse linear systems. Okay. For example, in this case, I am solving a simple two-dimensional Poisson equation in a square by using 2,500 unknowns, and in this case, the matrix, the related matrix, has a condition number that is 10 to 3, as an order of magnitude of 10 to 3. So the number of iteration of the conjugate gradient to obtain 5 digits of accuracy with respect to the initial residual, I started iteration by the null vector as a tentative solution. The number of iteration needed was 16. Okay? So if we consider a simple preconditioner for the matrix A based on the Cholesky factorization of the matrix that is able to reduce the condition number of 1 order of magnitude, allows us to obtain the same number of 5 digits in less than 20 iterations. So what is the precondition system? And what is the precondition? The precondition is a new matrix. In that slide, I put B to represent the precondition and apply a precondition result in solving a system that is related to the original system, but it is not exactly the same system. For example, in the case of BAX equal BB, I am using a left precondition. In this case, I am using a right precondition. And here, I am solving a system by using a two-side precondition. Matrix B and matrices B1 and B2 are approximation of the inverse of R, of A. Okay? Since the best situation is a situation in which the condition number is 1. So in this case, my objective is to obtain as a coefficient matrix a matrix that is as close as possible to the identity. Okay? So what is the way to attain a good precognition? This is a very active product, research context. What is a HPCG benchmark? Before to say you some details on the best way to obtain a good precognition, I have to say what is the way the top 500 team obtain the column related to the HPCG benchmark and the number of floating point rate obtained on this class of problems. Again, we have the Dongara and team that a few years ago told that HPC applications were not well represented by the LIMPAC benchmark, because they work on sparse problems and not on dense problems. There are many applications, for example, the traditional application related to partial differential equations that represent a context in which the bandwidth is more important than the operation speed. So the problem that HPCG solves is the Laplacian problem, that is the discretization of a 3D Poisson equation on a cube domain with the Dirichlet boundary condition. In this case, the stencil is 27 point stencil, using all the possible nodes that can be identified in a small cube representing a finite volume of a possible mesh on the cube domain. The process in data layout diciamo, sorry, speaking in Italian, the number of processes are logically decomposed in a 3D grid, and the total number of processes is then the product of the number of processes that I put in the 3 direction. And each processor owns a subset of matrix rho corresponding to a local domain. The idea is to have a small cube replicated on a total number of NP processes that are organized in a 3D process grid. Each process is identified by 3 different identifiers as in a 3D typical context. The solver is the precondition conjugate gradient and is the original SNF-Stiefel algorithm. And the precondition in the last release of the benchmark is a geometric multigrid they apply a V cycle. I explain you some details on the multigrid in a few minutes with the 3 levels, and they use one iteration of the symmetrized Gauss-Seidel smoother at each level. Symmetrized Gauss-Seidel method is a basic iterative method. Maybe you studied it. Is a version, a smarter version with respect to the classic Jacobi iteration, okay, based on a splitting, on a simple splitting of the matrix. So let's go deep inside the preconditional conjugate gradient algorithm to understand what is the operation intensity of this algorithm. You have a given solution that is a tentative solution. We compute a residual, a current residual, that is a vector obtained by matrix vector product. And you apply a precondition, and then iteratively you compute some constants that are obtained by different scalar products among vectors. You recognize three different HPC operations that are vector updates, and the application of the precondition at each iteration. Okay, so the main operation you do are precondition application, sparse matrix vector operation involving the original matrix, and you know that in a distributed setting, you can understand that in a distributed setting, a sparse matrix vector multiplication require only local data communication. And dot products and scalar products are killers for this type of algorithms, since a dot product in a distributed memory setting requires global synchronization among all the processes involved in the computation. Okay? So data movement on the network and global reduction. Actually, operations are very good since are parallel. Okay? Each process can compute on each bunch of data without communication on the network. So essentially, there is an intrinsic performance limit. We only do plus 1 and 2 operation, where the operation intensity is constant. So there is an intrinsic limit, and the problem is memory or communication bound. If we put this problem into the roof model, performance model. Okay, so we can do better. Can we do better from the point of view of algorithmic side? There is a lot of research on this. During the year, many people worked on this aspect and proposed some different algorithms. For example, there is a precondition version of the conjugate gradient based on an idea published by Romin and Azevedo in 1992 in order to reduce the global synchronization to 1 from 2, that is in the standard version of the algorithm, to 1. And this obtained by formulating the algorithms by recomputing some operation involved in the algorithm, the original algorithm, by using a recurrence in order to reuse the computation we already have done. Okay? In this way, we can obtain the scalar that are involved in the global synchronization, one from the other. So we can reduce the synchronization to 1. Another approach was proposed by Chronopoulos and Dier, and is related to block the iteration in order to find a new solution in the subspace, increasing in the Krylov subspace, increasing the dimension of subspace in block of S. So we can collect the matrix vector operation in S product by increasing the dimension of the Krylov space at each iteration S by S. Okay? In this way, the number of iterations is reduced, requiring the global synchronization is automatically reduced, and we can obtain all the dot products needed for updating the new solution from the old one in only one synchronization. So we reduce the number of synchronization in the order of ODS. Okay? This is the algorithm. This is a version of the conjugate gradient that we call the flexible for some numerical problems. It is. And what we can say that the main advantages of this algorithm is that all the scalars needed for updating the vectors that are the new direction and the new solution and the new residual can be done all together. So the global synchronization is only one. And there is another thing that we could observe, that we can reuse some data because, for example, the vector zeta is involved in all the three operations. So we can use data locality by leaving a zeta vector in the local memory of the threads, for example, on GPU, in order to reuse it in the best way the data, and doing this operation in a fast way on GPU, but also on CPU. Here we have the vector updates that are parallel, and there is the application of the preconditioner that is the main bulk of this computation. So we need to focus on the matrix B, okay, in order to have a good algorithm. In the case of precondition as a step, we have a similar approach in terms of algorithms since we need to compute the preconditional residual by applying vector B, and we have to compute all the new vector of the basis, of the Krylov basis, all together, doing some matrix product multiplication involving the product BA. Okay? So this kernel is called a matrix power kernel, and many people are working to do this computational building block in an efficient way when matrix B and A are very sparse. Also, in this case, we have some dot products that can be done all together by doing only one synchronization. There is a problem in this type of algorithms that increasing S, that is a good situation, since if we increase S, we reduce the number of global synchronization, but increasing S, algorithms can stall, the algorithms can stall, in the sense that convergence can be very slow, and sometimes you can also are in a situation in which your accuracy cannot be obtained. Okay, and so many people are working on improving stability of these algorithms in order to do in a situation that S can increase without losing numerical properties and the convergence. So what are multigrid methods? We are working on multigrid methods at SIAC. And multigrid is also the precondition context in which HPCG works. Okay. In the case of HPCG, since we have a mesh on which the Poisson equation is discretized, we can define a hierarchy of meshes by changing the discretization parameter and obtain a coarser matrix from the fine one. And we can define an algorithm that was introduced by Brandt in 17th, in which you can apply some basic iterations to the original matrix in order to obtain a tentative solution. So at the fine level, you can apply, for example, Jacobi or Gauss-Seidel. And you have some operators that are called prolongator and restrictor to move among the different mesh in a hierarchy, okay? So if you have a tentative solution, we can restrict this solution to a coarser level matrix, that is a coarser level space. You can reapply the smoother, that is the basic iterative method, again, Jacobi or Gauss-Seidel, as you want. You obtain a new solution on the coarse space, okay? And you can reiterate in a recursive way on different level of the matrix, of the mesh. At the coarsest level, you can obtain the solution of the related system, and you can go again down along the meshes, projecting the solution, improving the former solution obtained at that level by adding the prolongation, okay? Reiterate to improve again the current level solution by applying again Jacobi or Gauss-Seidel, and then correct the solution to final level at the end. This process is very efficient from the convergence point of view. What is the idea? The idea is that a smoother, that is a basic iterative process, is able to reduce some error components, but not all. The error components that are related to the small eigenvalues of the matrix are not well reduced at a given level. But when you go up on the different level, the so-called smoothing error components, that are the components that the smoother is not able to dump at a given level, become more oscillatory. And in the case of oscillatory components that correspond to the large eigenvalue of the current level matrix, can be dumped in a good way by the smoother. Okay? So I can move the solution at different mesh in order to use this type of hierarchy processes in order to dump all the components at different frequency in the different level. And then by projecting well this solution among the different levels, I can correct the final solution by obtaining better results. These methods can be, from one side, linear in terms of time complexity, so are optimal in many cases. And convergence can be optimal in the sense that increasing the dimension of the problem, the number of iterations needed to conjugate gradient when a multigrid is applied as precondition can be constant, almost constant. And this is the optimality in terms of convergence properties, and it is a key property to be scalable. Okay? We are working on algebraic multigrid that are another type of multigrid method where geometry is not available. And all the information needed to select the good smoother and to select the prolongator and the restrictor operator for moving among the different level of the spaces, or the vector spaces, since each mesh represents a vector spaces, is obtained only using information inside the matrix. Okay? If you have the matrix, you have all the needed information to select the good prolongator and the good restrictor in a multigrid process to have the multigrid hierarchy. And this type of multigrid are known as algebraic, in the sense that no geometry is needed to define them. Okay. So let me say that to obtain a scalable precondition, that is what we want in order to use supercomputers for solving a larger and larger problem. We need that optimality of the algorithm and of the precondition is not only optimality in terms of computational complexity, but optimality as to be an algorithmic optimality or scalability, and this is related to the possibility to obtain convergence whose properties don't change by increasing the dimension of the problem. And we need a nice degree of parallelism inside the matrix B. The matrix B has to be good in order to avoid to do, for example, global communication among data, okay? And in order to have the best operation intensity, so that I can use the single node and the memory on the single node in the best way. The best situation that we can have in the case of the sparse problem is that our precondition can be based on a hierarchy of matrix product vectors. You have seen that conjugate gradient, it is a basic algorithm, all the variants of the conjugate gradient as main operation in which communication is needed, also if it is local communication, so it's a good situation, it's the best situation you can have. So if also the matrix B is based on a hierarchy of operation represented by a hierarchy of matrix product, of a matrix vector products, we are in the best possible situation, okay? And algebraic multigrid or multigrid, generally speaking, is a good context because the main operation are matrix product vector or matrix vector products at each level. Okay, and it depends also on the choice of the type of a prolongator we can find and of the type of smoother that is basic iterative algorithms that we have to apply at each level. Okay, so we need to focus on the best possible smoother and on the best possible way to obtain a prolongator that are sparse and decoupled in the sense that they can have a diagonal block form, since if the prolongator has a diagonal block form, you don't have interaction among processes, and you can do matrix vector products needed to prolongate and to restrict the solution at each level of a multigrid locally on processes without global or any type of communication among processes. Okay, so we are working on this, and I have to finish, so I cannot go in details on our approach. I can say that we select some smoother that are the basic iterative algorithms that we have to apply at each level of a multigrid hierarchy to solve the system at each level. That is not the best one from the convergence point of view, since in many applications, the best convergence properties are obtained by applying Gauss-Seidel as a basic smoother. But Gauss-Seidel requires a sparse triangular solve at each application, since it requires to invert the lower part of the system matrix to obtain an update of the solution. And the sparse solvers are not so good in a parallel context. You know that backward or forward substitution are intrinsically sequential. Okay, so this is the case in which we prefer to have to apply a method that is less efficient in terms of convergence property, for example, Jacobi, or a weighted Jacobi, whose iteration matrix is diagonal, in order to use at the best, this is the matrix split it among different processors. And in the case of Jacobi, we are using only the diagonal to obtain the new solution at each iteration step. So this doesn't require any data communication among processes. And this is embarrassingly parallel. So we can apply this in a GPU context without context switch, and we can use at the best the floating point throughput of GPU in this type of high-level parallel smoother. And all we are doing in terms of research is already available in a version of our software that we called for many reasons Match GX. That is a version of a communication reduced algebraic multigrid for GPU accelerated multi-node systems. We are doing some benchmarks on Leonardo for this type of code. We run by using the same benchmark used in HPCG by increasing linearly the dimension, increasing the number of GPUs. And this is a picture in which we show that by using similar solvers implemented by NVIDIA, since NVIDIA proposed a library named AMGX that implement algebraic multigrid and conjugate gradient iterative algorithms to solve sparse linear systems. And here you can see that the blue line after 16.4 GPUs going up is better than the algorithms implemented in the NVIDIA library. Okay, these results are already published, and we were able to scale up to 2048 GPUs on Leonardo, and the solve time increased only of a factor with a factor 3 when the number of unknowns increased with a factor of more than 2,000, and we were able to obtain up to 35% of efficiency. That is very good and is very competitive with the state of the art. These are some references, the projects in which we are involved, and you can write me in order to have more information. Also because we are looking for young collaborators. We need to hire for new projects. We open, we currently have a new position open for this type of research in the context of a Center of Excellence for Supercomputing Application at European level. And if you want details on open positions, you can send an email to me when you want. I hope that it was not so boring. I thank you for attention.
Let's thank again our speaker.
Thank you.